So, we are continuing our discussion with DNA polymerase 3 and how it works on the lagging strand. Because remember, our lagging strand is the 5' to 3' strand, which means our complementary DNA or our new DNA that we have to make is going to be 3' to 5'. And our big DNA polymerase 3 restrictions were it must start on a 3' side of a primer, and it must build a 5' to 3' strand. So we can't just immediately have it running as if it were on the lagging or on the leading strand, right? So on the leading strand, our DNA polymerase would just be here, and it would just chuk. But here, if we tried that, that's the 5' side, we can't attach to there, and B, the sawmill is pushing this through so that you would be making 3 to 5 DNA, right? So 3 to 5 primer means when you start adding DNA, you're continuing to add in the 3 to 5 direction. So it must build in the 5 to 3 direction. So this is not going to work. Things have to be different. Different how, you might ask? Well, there's an easy way to get past this. It's just a two-step process. So, first off, polymerase 3 is a little bit distanced on the lagging strand. That's not something that's important to note, but it's just in a little bit of a different spot, right? And that's so that we can attach to a 3' side. So that's nice. That problem's solved. And then the other thing that happens that's much more important to be able to know is that, right, one of the big reasons this didn't work, aside from if it was right in the same spot attaching to a 5' side, which it can't do, the other big reason it doesn't work is that it's getting pushed through in this direction. But what if down here on the lagging strand, where it attaches to a 3' primer, what if we just run that strand backwards, right? So in other words, think of it like we push our string through this way, and then occasionally we just push our string the other direction, right? So separation is going this way. But when it reaches polymerase, we just push it the other direction briefly, right? And that's so that polymerase can bind to a 3' like it must. And if we just push it the other direction, temporarily, we'll be building in the 5 to 3 because remember, on the lagging strand, we have it, DNA running And we've got our strand. And as long as we just keep running DNA on our leading strand down here, as long as we just keep running DNA, our new strand will be being built in the 5-3. Well, if we briefly run it backwards, it'll look just like it is on the leading strand. So the reason multiple primers are put down is because on the lagging strand, we build new DNA between primers. Right? So this will attach here. My strand will temporarily push itself backwards, which is essentially doing the same thing on the leading strand, and we'll get a new bit of DNA. And then once that's made, it just lets go, and all we got to do is keep on keeping on, right? So our DNA will continue to get pushed so that we'll be able to get DNA polymerase 3 attached to the next primer. And then run it backwards and we'll build new DNA, right? So all we got to do is clink and run it backwards, because on the leading strand, it's just constantly running this direction, which is building a 5-3. So on that lagging strand, we just and then let it continue doing its thing until we get to the next primer, and then keep on keeping on. Right? So it's not too terrible. It's kind of like a trombone, right? So when you're playing a trombone, the slide goes out, the slide comes in. It's going both directions, right? So we're pushing our slide, and then occasionally we're changing the direction. So this is the trombone loop replication thing. And eventually what we're going to end up with is a lagging strand that has DNA in little stretches between primers. And our new vocab is Okazaki fragments. That is the DNA that's produced on the leading strand or lagging strand. So this is our lagging strand. And this is the way that we're able to make DNA using an enzyme that can only build in the 5'3" direction, right? Whereas on that leading strand, everything worked out nicely so that we only needed that one primer, and then we had fresh new DNA all the way down. So, not too bad. And this is DNA Polymerase 3. We've now talked about how it operates on the leading strand, and we've now talked about how it's able to build new DNA on the lagging strand, and that the new DNA is built as fragments of DNA between primers. So we have fragments of DNA between primers, Okazaki fragments. That's not too bad. And that's replication. Next up is going to be how we clean things up. Because, well, we've got a bunch of new DNA. Unfortunately, there's a whole bunch of RNA primers in there. And DNA, like our genomes, do not have chunks of RNA just interspersed all in there. Got to get rid of that and make it all DNA.